There's a silent war raging across the cosmos, one so vast, so ancient, that its battles unfold over billions of years. It's a conflict between two of the universe's most fundamental forces: gravity, the relentless pull that shapes galaxies and bends space itself, and light, the radiant energy that defies darkness and carries the secrets of the stars. This isn't a war of destruction, but of creation, a cosmic dance that has sculpted everything from the smallest atoms to the largest structures in existence. And today, we're going to uncover the incredible story of this eternal struggle and the breathtaking remnants it's left behind. Picture a black hole where gravity's grip is so overpowering that not even light can escape. It's a perfect example of this cosmic battle, a place where gravity wins, but not without consequences. The light that vanishes into its depths isn't truly lost. It leaves behind echoes, distortions in space-time that tell us stories of what once was. Across the universe, this same struggle plays out in countless ways. Galaxies spin and collide, their stars caught in the tug of war between gravity's pull and light's unstoppable journey. Even the very fabric of reality bears the scars of this conflict, from the warped paths of distant starlight to the mysterious dark matter that hints at gravity's hidden victories. But why does this matter to us? Because every time we look up at the night sky, we're witnessing the aftermath of this epic war. The constellations we trace, the auroras that dance, even the faint glow of the cosmic microwave background, they're all part of the legacy left behind by gravity and light. This isn't just a story about distant stars and abstract physics. It's a story about how the universe came to be the way it is, and how we, as curious explorers, are piecing together its secrets. So buckle up, because by the end of this journey, you'll never see the cosmos the same way again. The stage is set, the forces are at play, and the mysteries are waiting to be uncovered. Let's dive in. To understand this cosmic duel, we need to look at how these two forces operate on completely different scales. Gravity works slowly, patiently. Its influence builds over immense distances and time, pulling galaxies into clusters and shaping the large-scale structure of the universe. Light, on the other hand, is instantaneous by comparison, darting across space in the blink of an eye, carrying information from the farthest reaches of existence. Yet despite their differences, they're locked in an eternal dance. Take a star, for example. Its immense gravity crushes atoms together at its core, igniting nuclear fusion and unleashing torrents of light. That light pushes outward, fighting against gravity's inward pull, creating a delicate balance that keeps the star stable for millions or even billions of years. But when a massive star dies, gravity finally wins, collapsing it into a neutron star or black hole, where light is either bent into submission or trapped forever. These extreme objects become cosmic laboratories, showing us just how far this struggle can go. Yet light isn't powerless. Even when gravity bends its path, a phenomenon called gravitational lensing, the light still finds a way to reach us, twisting around galaxies and black holes to deliver distorted but breathtaking images of the distant universe. In a way, light bends the rules right back, using gravity's own warping of spacetime to magnify and reveal objects we'd never see otherwise. It's a perfect example of how these two forces don't just oppose each other, they also collaborate in unexpected ways, shaping the universe into the dynamic, evolving place we observe today. This cosmic tug of war has left its mark everywhere. The very expansion of the universe is a battleground. Gravity tries to slow it down, while the energy of light and other radiation pushes against it. And when we look at the faint afterglow of the Big Bang, we're seeing the echoes of a time when light finally broke free from gravity's grip, flooding the universe and allowing the first stars to shine. Every galaxy, every nebula, every flicker of starlight is part of this grand story, a story we're only just beginning to understand. Einstein's groundbreaking realization changed everything we thought we knew about gravity and light. He didn't just see gravity as a simple pull between objects, he envisioned it as the bending of space and time itself. Picture the universe as a vast, stretchy fabric. When you place something heavy, like a star or a black hole, onto that fabric, it creates a deep dimple. Now imagine light traveling across this warped surface. Instead of moving in a straight line, it follows the curve, just like a marble rolling around the edge of a bowl. This is why light bends near massive objects. It's not being pulled. It's simply following the contours of bent spacetime. One of the most famous proofs of this came during a total solar eclipse in 1919. Astronomers observed starlight bending around the sun, exactly as Einstein predicted. The positions of those stars appeared slightly shifted because their light had to travel along the sun's gravitational well, like a car taking a detour around a valley. This wasn't just a victory for Einstein's theory, it was direct evidence that gravity doesn't just pull on matter, it reshapes the very paths light takes through the cosmos. Today, we see this phenomenon everywhere. Galaxies and galaxy clusters act like cosmic magnifying glasses, warping the light from objects behind them in a process called gravitational lensing. Sometimes this creates stunning cosmic illusions, multiple images of the same distant quasar stretched into arcs or even perfect rings of light, like a celestial mirage. These distortions aren't just beautiful, they're tools. Astronomers use them to study dark matter, measure the universe's expansion, and even spot planets orbiting stars thousands of light years away. But the most extreme cases happen near black holes, where spacetime is bent so severely that light loops back on itself. Some photons get slingshotted around the black hole's edge, creating a glowing ring known as the photon sphere, a place where light orbits endlessly, caught in gravity's inescapable grip. Even here, though light fights back, some particles escape, carrying with them the black hole's shadow, a dark silhouette framed by a halo of warped starlight. This delicate interplay, where gravity distorts but doesn't completely silence light, shows us that their cosmic battle isn't about annihilation, it's about transformation. Every time we observe these phenomena, we're seeing Einstein's revelation in action. The universe isn't just filled with objects moving through space, it's a dynamic, ever-shifting stage where matter and energy bend the rules of reality itself. And as our telescopes grow more powerful, we're uncovering even stranger examples of this warped cosmic ballet, proving that gravity and light don't just oppose each other, they collaborate in ways we're still learning to decode. Black holes are the universe's ultimate victory for gravity, a place where even light, the fastest thing in existence, meets its match. These cosmic monsters form when massive stars collapse under their own weight, their cores crushed into an infinitely dense point called a singularity. The pull around this point is so intense that it warps space and time into a one-way trap, the event horizon. Cross that invisible boundary and there's no turning back, not even for light. It's like a cosmic waterfall. Once you pass the edge, the current drags you down with unstoppable force. But before light vanishes forever, it puts up a spectacular fight. As matter spirals into a black hole, friction heats it to millions of degrees, creating a glowing, swirling disk called an accretion disk. This is light's final act, a brilliant, high-energy performance before it's swallowed by the darkness. The disk shines across the electromagnetic spectrum, from radio waves to X-rays, revealing the black hole's presence even when the hole itself remains invisible. Some black holes, especially supermassive ones at the centers of galaxies, can outshine entire star systems with this radiant last stand. Yet even here, gravity has the final word. The light from the accretion disk isn't just glowing, it's distorted, stretched, and twisted by the black hole's immense pull. Photons emitted from the side of the disk spinning toward us appear brighter and bluer, while those on the far side, fighting against the black hole's drag, appear dimmer and redder. This phenomenon, called relativistic beaming, turns the disk into a lopsided halo of light, a cosmic funhouse mirror reflecting gravity's overwhelming power. And then there's the strangest twist of all: black holes don't just trap light, they can also fling it away. Some of the energy from the infalling matter gets channeled into jets, narrow beams of particles and radiation that shoot out from the poles at nearly the speed of light. These jets can stretch for thousands of light years, punching through galaxies and leaving behind glowing scars in the interstellar gas. It's a paradox. Even as the black hole devours everything nearby, it also becomes one of the universe's most powerful engines, shaping entire galaxies with its fury. What makes black holes so fascinating isn't just their destructive power, it's what they teach us about the limits of physics. Near the event horizon, time slows to a crawl. A distant observer would see a clock falling into the black hole tick slower and slower, freezing just as it crosses the threshold. Meanwhile, for the clock itself, time passes normally until the crushing tidal forces tear it apart. This eerie disconnect hints at something profound. Black holes aren't just objects. They're boundaries, places where the known laws of the universe stretch to their breaking point. And yet, even in their darkness, black holes leave clues. The way they bend light, the way they warp space, even the faint whispers of Hawking radiation, theoretical particles slowly leaking away over eons. All of it helps scientists piece together the puzzle of how gravity and light interact in the most extreme conditions imaginable. Every black hole we study is like a laboratory, testing our understanding of the cosmos in ways no earthbound experiment ever could. So while light may lose the battle at the event horizon, its struggle, and the echoes it leaves behind, illuminate some of the deepest mysteries of the universe. Neutron stars are where gravity shows off its most extreme feats, cosmic laboratories where the rules of physics get pushed to their breaking point. Imagine taking the mass of our sun and cramming it into a sphere no wider than a city. The result is so dense that a single teaspoon of its material would weigh billions of tons, collapsing atoms into a sea of neutrons so tightly packed that they behave like a single, bizarre quantum fluid. Here, gravity doesn't just bend light, it twists it into knots, warping reality itself into shapes we're only beginning to understand. Some neutron stars become pulsars, spinning hundreds of times per second while blasting beams of radiation across the cosmos like interstellar lighthouses. These beams sweep past Earth in precise clockwork flashes, so regular that astronomers once nicknamed them LGM signals, jokingly wondering if they were messages from little green men. But the truth is even stranger. Pulsars are the corpses of massive stars, their intense magnetic fields funneling energy into narrow jets that light up the universe with eerie precision. Each pulse is a heartbeat from a dead star, a reminder of gravity's relentless power to transform the familiar into the extraordinary. Then there are magnetars, neutron stars with magnetic fields so strong they could erase a credit card from halfway across the solar system. These fields strain the star's crust to the point of breaking, triggering starquakes that release bursts of X-rays and gamma rays powerful enough to light up Earth's upper atmosphere from thousands of light years away. In 2004, a magnetar flare briefly outshone the full moon, even though its source was 50,000 light-years distant. Gravity's grip here is so overwhelming that it bends not just light, but space itself, creating an environment where the laws of physics as we know them start to fray at the edges. What's truly mind-bending is how light behaves near these objects. A neutron star's gravity is so intense that if you could stand on its surface, which you couldn't, since you'd be instantly flattened into a thin smear of atoms, the sky above would look like a funhouse mirror. Light from stars directly overhead would appear slightly shifted, while those near the horizon would be stretched into smears or even duplicated, as gravity bends their light around the star in multiple paths. It's as if the universe itself is being stretched and folded like dough, with light tracing the contours of this warped reality. Yet even in these extreme conditions, light fights back. The charged particles swirling around neutron stars emit radiation across the spectrum, from radio waves to gamma rays, painting the cosmos with signatures of their defiance. Some neutron stars even fling matter outward at nearly the speed of light, creating glowing nebulae that pulse with energy long after the star's explosive birth. These remnants are more than just cosmic oddities. They're proof that even in gravity's strongest grip, light finds a way to leave its mark. Studying neutron stars isn't just about unraveling the mysteries of stellar corpses. It's about testing the very laws that govern our universe. Their extreme densities let scientists probe states of matter that can't be replicated on Earth, while their precise pulses serve as natural laboratories for studying general relativity. Every flicker, every burst, every warped beam of light carries clues about how gravity and light shape the cosmos, and how, in their endless duel, they've written the story of everything we see. Gravitational waves are the universe's way of whispering its most cataclysmic secrets, ripples in the fabric of space-time itself, sent racing across the cosmos at the speed of light. These waves aren't born from gentle events. They're the shockwaves of chaos unleashed when black holes spiral into one another, neutron stars tear each other apart, or massive stars collapse in supernova. Picture tossing a pebble into a pond. The ripples spread outward, distorting the water's surface. Now imagine that pebble is a black hole 30 times the mass of our sun, and the pond is the very structure of reality. That's the scale of these cosmic tremors. For decades, gravitational waves existed only in theory, a prediction of Einstein's general relativity that seemed almost too subtle to ever detect. Then, in 2015, humanity's technological ingenuity caught up with Einstein's genius. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by capturing the faintest distortion, a wave stretching and squeezing space by less than 1,000th the width of a proton. The signal came from a pair of black holes, each dozens of times heavier than our sun, locked in a death spiral over 1 billion light-years away. Their final collision released more energy in a fraction of a second than all the stars in the observable universe combined, warping space-time so violently that the ripples still reached us over 1 billion years later. What's astonishing isn't just that we detected these waves, it's what they tell us. Gravitational waves carry fingerprints of their origins. The pitch and strength of the signal reveal the masses of the colliding objects, how fast they were spinning, even the direction they were moving. It's like listening to a cosmic drumbeat and reconstructing the entire drum, the shape, the material, the force of the strike from the sound alone. In 2017, another breakthrough came when LIGO detected ripples from colliding neutron stars. This time, telescopes around the world saw the aftermath, a glowing kilonova explosion that forged heavy elements like gold and platinum, scattering them across space. For the first time, we'd heard and seen the same event, opening a new era of multi-messenger astronomy. But the real magic lies in what these waves can reveal about gravity itself. Near merging black holes, spacetime is warped so violently that Newton's laws of motion break down entirely. Gravitational waves let us test Einstein's equations in these extreme regimes, probing whether relativity holds up or if new physics lurks in the shadows. Some waves might even carry echoes from the Big Bang, traces of primordial black holes or cosmic strings left over from the birth of the universe. Every detection peels back another layer, showing us a cosmos far more dynamic and violent than we ever imagined. A place where spacetime itself rings like a bell, echoing with the footsteps of invisible giants. And this is just the beginning. New detectors like the space-based LISA mission planned for the 2030s will listen for lower frequency waves from supermassive black holes merging at the hearts of galaxies. Others might catch the faint murmurs of neutron stars quaking or the background hum from countless collisions across cosmic time. With each ripple we capture, we're not just observing the universe, we're feeling it, tracing the invisible contours of gravity's battlefield in a way light alone could never show us. The era of gravitational wave astronomy has opened a window into the darkest, most energetic corners of existence, where the very rules of reality are written in the tremors of space-time. Dark matter is gravity's silent ally, an invisible force weaving the cosmic web that holds the universe together. Unlike stars or galaxies, it doesn't shine, reflect, or absorb light, yet its gravitational fingerprint is everywhere. Take a spiral galaxy like our Milky Way. If you calculated its mass based on the visible stars and gas alone, the math wouldn't add up. The outer stars orbit far too quickly, as if some unseen anchor is tugging at them, keeping them from flying off into the void. That anchor is dark matter, an enigmatic substance outweighing ordinary matter 5-to-1. Its gravity sculpting galaxies into the shapes we recognize and binding clusters together like cosmic glue. The evidence for dark matter isn't just in spinning galaxies. It's written in the bent light of distant objects. When astronomers study massive galaxy clusters, they often find that the light from galaxies behind them is distorted into arcs and rings, far more than the visible mass could explain. It's as if space itself is lined with hidden weights, warping the path of light like a lens made of shadows. These gravitational mirages, called Einstein rings, reveal the true scale of dark matter's influence. Without it, galaxy clusters would fly apart, and the universe's large-scale structure, the vast filaments and voids we see in cosmic maps, would never have formed. But what is dark matter? The leading theory suggests it's made of particles that barely interact with light or ordinary matter, passing through stars and planets like ghosts. Imagine a crowded room where most people are invisible. You'd only know they're there by the way they subtly nudge the visible ones. That's how dark matter behaves, its presence felt solely through gravity's pull. Some experiments, like those in deep underground labs, hunt for rare collisions between dark matter particles and atoms, hoping to catch a fleeting whisper of this elusive substance. Others scan the skies for anomalies in gamma rays or the cosmic microwave background, searching for indirect clues. The irony is profound. Dark matter, which emits no light, has shaped the universe into a stage where light can thrive. In the early cosmos, its gravitational wells gathered gas and dust, seeding the first galaxies and stars. Without it, the night sky might be nearly empty, with stars scattered too thinly to ignite the complex chemistry that makes life possible. Yet for all its importance, dark matter remains one of physics' greatest mysteries. Is it a single type of particle or a family of them? Does it interact with itself in ways we haven't detected? Could it even be tied to extra dimensions or other exotic physics? Every unanswered question about dark matter is a reminder of how much gravity still hides from us. While light paints the universe in vivid detail, dark matter's shadowy presence proves that gravity, in its quiet persistence, holds the real power to shape existence. And as telescopes peer deeper into the cosmos and detectors grow more sensitive, we're inching closer to uncovering the secrets of this invisible architect, the force that tipped the cosmic scales in gravity's favor, leaving its mark on everything from the smallest dwarf galaxy to the grandest superclusters in the sky. If gravity is the cosmic glue holding the universe together, dark energy is the invisible hand tearing it apart, an anti-gravity force so baffling that it makes dark matter seem straightforward by comparison. While dark matter's gravity sculpts galaxies and clusters, dark energy operates on the grandest scale of all, stretching the very fabric of space itself. Its discovery in the late 1990s sent shockwaves through astronomy, revealing that the universe isn't just expanding, it's accelerating, with galaxies flying away from each other faster and faster as time goes on. This wasn't just unexpected. It overturned decades of assumptions, forcing scientists to confront a reality where gravity, for all its might, isn't the only player in the cosmic tug-of-war. The clues began with distant supernovae. Astronomers expected these exploding stars to act as cosmic speedometers, revealing how much the universe's expansion had slowed since the Big Bang. Instead, they found the opposite. The light from these explosions was fainter than it should have been, as if space had stretched even more than predicted during the light's journey. The implication was staggering. Some unseen force was pushing the universe apart, overpowering gravity's pull on the largest scales. Further studies of galaxy clusters and the cosmic microwave background confirmed it. Dark energy makes up roughly 68% of the universe's total energy, dwarfing both ordinary and dark matter. It's as if the cosmos is saturated with an invisible pressure, a kind of negative gravity embedded in the vacuum of space itself. So what is dark energy? The leading explanation points to Einstein's cosmological constant, a term he originally added to his equations to keep the universe static, later calling it his greatest blunder when expansion was discovered. Ironically, it might have been his greatest insight after all. Quantum physics suggests that empty space isn't truly empty. It seethes with virtual particles flickering in and out of existence. These fleeting fluctuations could generate repulsive energy, a sort of cosmic background tension that drives expansion. But here's the problem. When physicists calculate how much energy this quantum foam should produce, the number is a staggering 120 orders of magnitude too large. If their math were right, the universe should have ripped itself apart instantly after the Big Bang. Clearly, something fundamental is missing from our understanding. Alternative theories abound. Some propose that dark energy isn't constant but evolves over time, a dynamic field nicknamed quintessence, after the ancient Greek term for the fifth element. Others suggest gravity itself behaves differently on cosmic scales, requiring modifications to Einstein's relativity. Then there's the spine-chilling possibility that dark energy's strength could increase indefinitely, leading to a Big Rip scenario, a future where not just galaxies, but stars, planets, and even atoms are torn apart by runaway expansion. Yet for all its mystery, dark energy's fingerprints are everywhere. It determines the universe's fate, deciding whether gravity will eventually reverse expansion in a big crunch, or if the cosmos will end in cold, empty isolation. Even now, its push overwhelms gravity's pull beyond our local cluster of galaxies, meaning most of the universe will one day disappear beyond an unreachable horizon. The light from those distant galaxies will stretch into oblivion, their stories lost to the void. This invisible force reminds us how much we still don't understand about the cosmos. Dark energy isn't just another puzzle, it's a glaring signpost pointing to gaps in our knowledge, a challenge to reconcile quantum mechanics and gravity into a single, coherent theory. Every observation, from the largest galaxy surveys to the faintest echoes of the Big Bang, brings us closer to unraveling its secrets. And as we peer deeper into the accelerating universe, one truth becomes clear. The final chapter of the cosmic war between gravity and light may ultimately be written by this enigmatic, unstoppable force. The story of gravity and light's cosmic duel begins in the searing heat of the Big Bang itself, a moment when the universe was too hot, too dense for either force to fully take hold. Picture a newborn cosmos, less than a second old, where space is a swirling ocean of energy so intense that particles and antiparticles flicker in and out of existence. In this primordial inferno, light isn't yet the radiant beams we know. It's trapped, tangled in a thick soup of charged particles called plasma. Every photon, every particle of light is instantly absorbed and re-emitted, unable to travel more than a fraction of an inch before being swallowed again. Meanwhile, gravity is already at work, subtly gathering denser regions of this chaotic broth, laying the groundwork for everything to come. For hundreds of thousands of years, this stalemate holds gravity pulling, light pushing, neither able to break free. Then, in a cosmic blink, everything changes. As the universe expands and cools, electrons and protons finally combine to form neutral hydrogen atoms. Suddenly, light has an escape route. With no charged particles to trap it, the universe goes transparent in an instant, a flashbulb moment astronomers call recombination. The once trapped photons burst free, streaming outward in all directions. This is the birth of the cosmic microwave background, the oldest light we can see, a snapshot of the universe at just 380,000 years old, stretched by expansion into faint microwave whispers that still fill the sky today. Yet even as light wins its freedom, gravity is already shaping the next phase of the battle. Those subtle density variations, the ones gravity nurtured in the plasma, now become the seeds of structure. Slightly denser regions pull in more matter, growing heavier, their gravitational tug strengthening over millions of years. Gas collects, heats up, and collapses under its own weight until, in hearts of darkness, the first stars ignite. Their light is a revolution, a piercing blue radiance that tears through the cosmic fog, reionizing hydrogen and ending the universe's so-called dark ages. This is light's counterattack, photons so energetic they strip electrons from atoms, carving transparent bubbles in space where future starlight can travel unimpeded. The echoes of that first clash are everywhere. In the cosmic microwave background's faint temperature variations, we see the imprint of gravity's early fingerprints, regions where matter was ever so slightly denser, destined to become galaxies. In the distribution of galaxies across the sky, we trace how gravity sculpted light's escape routes, weaving the vast cosmic web. Even the ratio of hydrogen to helium in the universe today is a relic of that fiery epoch, when light and gravity fought for dominance in a universe young enough to remember its own birth. What's astonishing isn't just that these forces shaped the past, it's how their struggle continues to define the present. Every star that shines is a testament to their uneasy truce, a balance between gravity's inward crush and light's outward pressure. Every galaxy cluster, every wandering photon, every ripple in spacetime carries the legacy of that primordial battle. The Big Bang didn't just set the universe in motion, it wrote the rules for an eternal dance, one where gravity builds the stage and light paints the scenery, each shaping the cosmos in ways we're only beginning to decode. The cosmic microwave background is light's oldest love letter to the universe, a whisper from a time when everything was just beginning. This faint glow, barely warmer than absolute zero, is the cooled remnant of the Big Bang's fiery dawn, stretched and diluted over nearly 14 billion years of cosmic expansion. But don't let its subtlety fool you. This afterglow is one of the most powerful tools we have for unraveling the universe's origin story, a snapshot frozen in time when light first broke free from gravity's grip. What makes this radiation so special is its near-perfect uniformity, a telltale sign of the universe's scorching infancy. No matter where we point our telescopes, the cosmic microwave background appears almost identical in every direction, varying by less than 1 part in 100,000. That uniformity is a relic of a time when space was so dense and hot that matter and radiation were locked in a violent embrace, constantly colliding until the universe cooled enough for atoms to form. When that finally happened, light could travel unimpeded for the first time, streaming outward in a brilliant flash that still lingers as this microwave haze. But look closer, and the cosmic microwave background reveals something even more profound: tiny fluctuations, patches where the temperature is ever so slightly higher or lower. These imperfections are gravity's fingerprints. In the early universe, quantum fluctuations created minute differences in density, regions where matter was a tiny bit more crowded. Over time, gravity amplified those differences, pulling more matter into the denser areas until they grew into the galaxies and galaxy clusters we see today. The cosmic microwave background is literally a map of where gravity began weaving the cosmic web, marking the spots where light's journey was subtly altered by the tug of matter. Some of these fluctuations are so large they defy simple explanations. The cold spot, a mysteriously frigid patch in the cosmic microwave background, spans hundreds of millions of light years. One theory suggests it's the shadow of a cosmic void, a vast emptiness where gravity's pull is weaker, stretching light's wavelength and cooling it as it travels through. Others propose even wilder ideas, like a collision with another universe during inflation. Whatever the truth, these anomalies remind us that light's ancient echo still holds puzzles we're only beginning to solve. Perhaps the most astonishing thing about the cosmic microwave background is how it bridges the gap between gravity and light. The same radiation that marks light's liberation also encodes gravity's earliest work, a dual record of how these forces shaped the cosmos. By studying its patterns, we've confirmed the universe's age, measured its composition, and even glimpsed the shadow of dark matter woven into its fluctuations. This faint glow isn't just a relic, it's a Rosetta Stone, translating the universe's first moments into a language we can finally understand. And the story isn't over. New telescopes like the James Webb Space Telescope and next-generation ground observatories are probing the cosmic microwave background with unprecedented precision, hunting for even fainter ripples that might reveal gravitational waves from the Big Bang itself. Every new observation peels back another layer, showing us how light, even when stretched and faded by time, never stops carrying secrets from the dawn of existence. Quasars are the universe's ultimate powerhouses, cosmic lighthouses so brilliant they outshine entire galaxies from billions of light years away. At their hearts lies a supermassive black hole, millions to billions of times the mass of our Sun, gorging on gas, dust, and even entire stars. But here's the twist: while black holes are famous for trapping light, quasars prove that light doesn't go quietly. These dazzling beacons are the result of gravity and light locked in an explosive showdown, where matter doesn't just vanish, it fights back with a fury that lights up the cosmos. Picture a star or gas cloud spiraling toward a supermassive black hole. As it gets closer, tidal forces stretch and shred it into a swirling disk of superheated plasma, glowing white-hot as it accelerates to nearly the speed of light. Friction within this accretion disk heats the material to millions of degrees, unleashing torrents of X-rays, gamma rays, and visible light. But the real spectacle happens above and below the disk, where magnetic fields twist into colossal jets, launching particles outward at nearly light speed. These jets can stretch for hundreds of thousands of light years, punching through intergalactic space like searchlights from the dawn of time. What makes quasars so fascinating is their sheer defiance. Even as gravity crushes matter toward oblivion, the energy released in the process becomes one of the most luminous phenomena in existence. A single quasar can emit thousands of times more light than the Milky Way, all from a region no larger than our solar system. It's as if the universe packed the energy of 1 trillion stars into a pinpoint, a testament to how efficiently gravity can convert matter into raw radiation. Yet quasars aren't just relics of the past. They're snapshots of a violent, formative era when galaxies were young and black holes feasted greedily on the surrounding chaos. Today, most supermassive black holes, including the one at the center of our galaxy, are quiet, their fuel largely depleted. But quasars remind us that this calm is temporary. Given enough gas and stars to consume, even dormant giants can reawaken, reigniting the ancient battle between gravity's pull and light's escape. The light from these distant monsters carries more than just energy, it carries history. By studying quasars, astronomers have mapped the universe's structure, traced the distribution of invisible gas between galaxies, and even clocked the expansion of space itself. Their beams act like backlights, illuminating the cosmic web's faint filaments and revealing elements forged in the hearts of dying stars. In a way, quasars are both destroyers and creators, their fury seeding the universe with the heavy atoms that make planets and life possible. But perhaps their greatest lesson is one of perspective. When we look at a quasar, we're seeing the universe at its most extreme, where the laws of physics are pushed to their limits. These brilliant beacons prove that even in gravity's strongest grip, light finds a way to roar back, shaping the cosmos as dramatically as the forces trying to contain it. They're not just remnants of a war-torn universe, they're proof that conflict, on a cosmic scale, can forge the most breathtaking wonders. Gamma-ray bursts are the universe's most violent tantrums, explosions so powerful they outshine entire galaxies in the blink of an eye. Imagine compressing the energy of 1 billion suns into a beam no wider than a pencil, then firing it across the cosmos at nearly the speed of light. These bursts are light's last, desperate stand against gravity's relentless pull, a final blaze of glory before being swallowed by the darkness. Most gamma-ray bursts begin with the death of a massive star, 12 of times heavier than our Sun. As the star exhausts its nuclear fuel, gravity seizes its chance, crushing the core inward with unstoppable force. In less than a second, the core collapses into a black hole or neutron star, releasing a shockwave that rips the rest of the star apart. But here's where light fights back. Twin jets of plasma, hotter than anything in the universe, punch through the dying star's outer layers, accelerated by intense magnetic fields. These jets funnel the star's remaining energy into narrow beams of gamma rays, light so energetic it can ionize atoms from thousands of light years away. The numbers are staggering. A single gamma-ray burst can release more energy in 10 seconds than our Sun will emit over its entire 10 billion-year lifespan. If one occurred within a few thousand light-years of Earth, the radiation could strip away our ozone layer, triggering mass extinctions. Thankfully, most bursts happen in distant galaxies, their light traveling billions of years before reaching us as faint, flickering signals. Yet, even at these distances, they're impossible to ignore. Satellites designed to monitor nuclear tests in the 1960s first detected gamma-ray bursts by accident, their instruments overwhelmed by flashes of radiation coming from deep space. But not all bursts are created equal. Some last mere milliseconds, likely caused by the collision of neutron stars, cosmic wrecking balls spinning into each other and unleashing gravitational waves alongside their brilliant firework display. Others, known as long-duration bursts, stretch for minutes, their afterglows lingering in X-rays and visible light for days or weeks. These longer bursts are the dying cries of hypergiant stars, their cores collapsing into black holes while their outer layers are torn apart in a supernova so bright it can outshine its host galaxy. What makes gamma-ray bursts so fascinating isn't just their power, it's what they reveal about the universe's most extreme environments. The jets responsible for these bursts are laboratories of physics we can't replicate on Earth, where particles are accelerated to energies far beyond anything in our largest colliders. Their light carries clues about the early universe, too. Some of the most distant bursts ever detected erupted when the cosmos was less than 1 billion years old, offering glimpses into an era when the first stars and galaxies were just beginning to form. And then there's the irony. These explosions, born from gravity's most destructive act, become beacons that help us map the cosmos. Astronomers use gamma-ray bursts to probe the vast clouds of gas between galaxies, measuring how their light is absorbed to trace the distribution of matter across the universe. They've even helped test Einstein's theory of relativity, confirming that light of all energies travels at the same speed, a fact that holds true even across billions of light years. In the end, gamma-ray bursts are a reminder that light doesn't surrender quietly. Even as gravity wins the battle, collapsing stars into black holes or crushing neutron stars together, light retaliates with a fury that echoes across the cosmos. These bursts are more than just explosions, they're cosmic road signs, pointing us toward the most violent, energetic, and mysterious corners of existence. And with every new detection, we're piecing together the story of how gravity and light shape the universe, one cataclysmic flash at a time. White dwarfs are the universe's quiet farewells, stellar embers glowing softly against the cosmic night. These remnants, no larger than Earth but packing half the mass of our Sun, are what remain when stars like ours exhaust their nuclear fuel. Unlike the violent deaths of massive stars that collapse into black holes or neutron stars, white dwarfs represent gravity's patient, inevitable victory, a slow squeeze so delicate it's held at bay by the sheer stubbornness of quantum physics. At their core, white dwarfs are supported by electron degeneracy pressure, a quantum quirk that prevents electrons from being crushed any closer together. Picture a crowded elevator where no one can move no matter how much weight presses down. The laws of physics won't allow further collapse. This balance between gravity's inward pull and quantum forces pushing back creates a celestial equilibrium, a stable but fading glow. Over trillions of years, these cosmic cinders will cool and dim, their light draining away like the last warmth from a dying campfire. Yet even in their stillness, white dwarfs tell a story of defiance. Their surfaces, though no longer fueled by fusion, still blaze at tens of thousands of degrees, radiating leftover heat from their former lives. Some are wrapped in intricate shells of gas planetary nebulae, the shed outer layers of their parent stars, illuminated by the dwarf's ultraviolet glow like neon signs in the void. Others, if paired with a companion star, may siphon material onto their surfaces, triggering periodic nova explosions that briefly reignite their brilliance. The most fascinating thing about white dwarfs isn't just their fate, it's what they leave behind. Their cores are crystallized carbon and oxygen, diamonds the size of planets forged under unimaginable pressure. Given enough time, these fading stars will solidify entirely, becoming cold, dark spheres adrift in space, but time on that scale is almost poetic. The universe isn't even old enough for the first white dwarfs to have cooled completely. The oldest still flicker faintly, their light a whisper from an era long before Earth existed. In a way, white dwarfs are cosmic time capsules. Their composition reveals the nuclear fusion recipes of their parent stars, while their slow cooling rates help astronomers measure the age of the galaxy. Some even carry traces of shredded planets in their atmospheres, debris from solar systems that once orbited them, now vaporized and mixed into their fading light. This gentle fade out is a reminder that not all cosmic battles end in explosions or oblivion. Sometimes gravity's victory is quiet, a slow dimming that takes eons. And as these stellar ghosts drift through the void, they carry with them the last light of stars that once shone brightly, proof that even in darkness the universe remembers. The fate of light in our expanding universe is a story written in invisible ink, one that unfolds over timescales so vast they dwarf human comprehension. Right now, as you read these words, photons from distant galaxies are racing through the cosmos, their wavelengths slowly stretching as space itself expands beneath them. This phenomenon, called cosmological redshift, is light's silent protest against the universe's relentless growth, a stretching that transforms once vibrant starlight into faint whispers of infrared and radio waves before fading into near nothingness. But redshift isn't the only force working against light. Dark energy, that mysterious repulsive force accelerating the universe's expansion, is pulling cosmic regions apart faster than light can bridge the gap. Imagine two ants on opposite ends of a stretching rubber band. The more the band stretches, the harder they must crawl to reach each other. Now replace those ants with galaxies and the rubber band with the fabric of space-time itself. For light traveling between them, this means an exhausting journey where the finish line keeps moving farther away. In time, galaxies beyond our local cluster will vanish beyond an unreachable horizon, their light stretched beyond detection, leaving future civilizations with a sky nearly empty of stars. Yet gravity isn't surrendering without a fight. Within galaxy clusters, its pull is strong enough to resist dark energy's expansion, creating cosmic islands where light still flows freely. These gravity-bound oases like our Milky Way and its neighbors in the local group will remain illuminated long after the rest of the universe disappears from view. But even here, light faces a slow decay. Stars will exhaust their fuel, white dwarfs will cool into black dwarfs, and eventually, the last flickering embers of stellar light will wink out, leaving only the faint glow of black hole evaporation Hawking radiation to punctuate the darkness. There's a haunting beauty to this distant future. The very photons that once painted the cosmos in color, the blues of young stars, the reds of dying giants, will have stretched into wavelengths longer than the observable universe itself. The cosmic microwave background, that ancient afterglow of the Big Bang, will redshift into silence, its whispers lost to the void. Even the evidence of our universe's greatest explosions, gamma-ray bursts, supernova, quasars, will dissolve into undetectable radio waves, erasing their stories from the sky. But light's legacy might not end in oblivion. Some theories suggest that in a universe dominated by dark energy, quantum fluctuations could spawn new Big Bang's pocket universes where light is born anew. Others speculate that advanced civilizations could harness black holes or other exotic physics to create artificial light sources, defying the cosmic dusk. While these ideas border on science fiction, they remind us that light's story is intertwined with the universe's deepest mysteries. a tale where even the inevitable can be rewritten by forces we've yet to discover. For now, we live in light's golden age, a fleeting moment when the cosmos is still ablaze with stars, and the night sky tells 1,000 stories. Every photon we detect, from the nearest street lamp to the farthest quasar, is a messenger from gravity's battlefield, a fleeting signal in the eternal struggle between darkness and illumination. And as we watch distant galaxies redshift into the void, we're not just witnessing light's fate, we're glimpsing the universe's final, unread chapter. Gravitational lensing is the universe's ultimate sleight of hand, a cosmic illusion where gravity twists the fabric of space so dramatically that light bends around it like water flowing around a stone. This phenomenon, predicted by Einstein over a century ago, turns massive galaxies and black holes into natural telescopes, magnifying and warping the light of objects hidden far behind them. The result, a celestial funhouse mirror that distorts reality while revealing secrets we'd never see otherwise. One of the most breathtaking examples is the Einstein cross, a quasar so perfectly aligned behind a foreground galaxy that its light splits into 4 distinct images, arranged like petals around the galactic core. Without the galaxy's gravity acting as a lens, this distant quasar would be far too faint to study in detail. But thanks to this cosmic magnifying glass, astronomers can analyze its light for clues about black hole behavior, galaxy formation, and even the distribution of dark matter woven through the lensing galaxy. Then there's the Hubble Space Telescope's iconic Frontier Fields project, where galaxy clusters like Abell 1689 became natural lenses to probe the early universe. The cluster's immense gravity warps space so severely that distant galaxies behind it appear stretched into luminous arcs, some magnified dozens of times their normal brightness. Among these smeared streaks of light, scientists have spotted galaxies from just a few 100 million years after the Big Bang, their youthful glow preserved by gravity's distortion. It's like finding a fossil buried under layers of rock, only to realize the rock itself has polished the fossil into perfect view. But gravitational lensing isn't just about magnification, it's also a forensic tool for uncovering the invisible. When astronomers map the distorted shapes of background galaxies, they can reconstruct the mass distribution of the lensing object, including its dark matter halo. Some lenses reveal ghostly rings, like the glowing signature of B1938+666, where a massive galaxy cluster bent a single background galaxy's light into a near-perfect circle. Others, like the galaxy nicknamed the Dragon, twist their background light into intricate fire-breathing shapes that hint at clumps of dark matter lurking within. What makes this phenomenon so revolutionary is its versatility. Weak lensing, where the distortions are subtler, lets astronomers measure the universe's large-scale structure and even test theories about dark energy's influence on cosmic expansion. Microlensing, on the other hand, can spot rogue planets floating between stars or reveal hidden stellar companions, their presence betrayed by brief flickers in a background star's light. The irony is profound. Gravity, the force that traps light in black holes and weighs down the cosmos, also gifts us these windows into the unseen. Every warped galaxy, every stretched arc, is a testament to the duality of these fundamental forces: gravity bending, light enduring, and together, painting a portrait of the universe richer than either could alone. And as telescopes grow more powerful, these natural lenses will keep pushing our view farther back in time, revealing corners of existence where gravity's grip is still shaping the story of everything. Time doesn't tick the same everywhere in the universe. Gravity sees to that. Near a massive object like a black hole or even our own planet, time slows down in a phenomenon called gravitational time dilation. This isn't science fiction. It's a measurable reality, proven by atomic clocks ticking at slightly different rates depending on their altitude. A clock on a mountain runs faster than one at sea level because gravity's grip weakens with distance, loosening its hold on time itself. Even GPS satellites orbiting Earth have to account for this effect. Their clocks speed up just enough that, if left uncorrected, your navigation would drift off by miles within minutes. But the real mind-bender happens when gravity reaches extreme levels. Near a black hole's event horizon, time slows to a crawl compared to the outside universe. An astronaut falling toward the black hole might experience mere minutes while centuries pass for distant observers. This warping of time isn't just a quirk, it reshapes how light behaves too. Photons struggling to escape a black hole's pull don't just lose energy. Redshifted to longer wavelengths, they also appear to freeze from an outsider's perspective, their final moments stretched into eternity. It's as if gravity isn't just bending space but weaving time into its fabric, creating a cosmic trap where even light speed can't break free. The implications ripple across the cosmos. When we observe stars orbiting the supermassive black hole at our galaxy's center, their light carries the stamp of this time warping. As they swing close to the black hole's immense gravity well, their light redshifts and their orbits seem to slow, not because the stars themselves are moving sluggishly, but because their very seconds are stretched. This eerie slowdown is gravity's signature, a reminder that the battle between light and gravity isn't just about space, it's a duel over time itself. And here's the twist: time dilation isn't one-sided. While gravity slows time near massive objects, the universe's expansion, driven by dark energy, speeds it up in the vast, empty voids between galaxies. Light traveling these cosmic deserts experiences less gravitational drag, its journey subtly altered by the competing tugs of gravity and expansion. The result: a universe where time flows at different rates depending on where you stand, a patchwork of temporal zones stitched together by the interplay of these fundamental forces. This temporal tug-of-war leaves its mark on everything we observe. The light from distant supernova appears to dim not just because of redshift, but because the universe's expansion has subtly stretched the duration of their explosions. Even the cosmic microwave background, that ancient echo of the Big Bang, carries imprints of regions where time once flowed slower or faster, frozen in the faint glow of the early cosmos. Every photon we detect is a messenger from a battlefield where time itself is the prizer, and gravity, the force that holds the clock hands in its grasp. Quantum gravity is the final frontier in the war between light and gravity, a realm so small, so strange, that the rules we know shatter into uncertainty. Picture the universe at the scale of an atom's nucleus, where gravity should be just another force tugging on particles. But here's the problem: Einstein's relativity, which explains gravity beautifully on cosmic scales, clashes violently with quantum mechanics, the rules governing the tiny world of particles and light. The result: a battlefield where neither theory surrenders, leaving scientists scrambling for a deeper truth, one that might finally unite these warring forces under a single law. String theory is one of the most ambitious attempts to broker this peace. It proposes that the fundamental particles we know, quarks, electrons, even the photons carrying light, aren't dots at all, but tiny, vibrating strings. These strings thrum at different frequencies, much like guitar strings producing distinct notes, and their vibrations determine whether they manifest as gravity, light, or matter. In this symphony of the cosmos, gravity isn't a force separate from light, it's just another note in the same grand composition. The theory even suggests hidden dimensions, curled up so tightly we'd never notice them, where gravity might gain the strength it lacks in our familiar three-dimensional world. But string theory isn't alone in this quest. Loop quantum gravity takes a radically different approach, imagining spacetime itself as woven from a network of tiny, interconnected loops. Think of the universe as a cosmic tapestry, where gravity emerges from the way these loops twist and knot together. Unlike string theory's extra dimensions, loop quantum gravity keeps things grounded in the space and time we know, just quantized, pixelated into the tiniest possible bits. Here, even the fabric of reality has a smallest possible unit, a quantum of space, preventing gravity from becoming infinite at the heart of black holes or the Big Bang. The stakes couldn't be higher. Without a theory of quantum gravity, we hit a wall when trying to understand the universe's most extreme moments, the singularity inside a black hole, or the first instant of the Big Bang. These are places where gravity and light should both reign supreme, yet our current laws crumple into nonsense. Some physicists even speculate that resolving this clash could unlock secrets about dark energy or the true nature of time itself. For now, the battle rages on. Experiments are hunting for clues, from particle colliders searching for extra dimensions to telescopes probing the afterglow of the Big Bang. Every flicker of a black hole's shadow, every anomaly in quantum experiments, could be a hint toward the ultimate theory. One day, we might find that gravity and light were never truly at war, just two sides of a coin we hadn't flipped over yet. Until then, the search for quantum gravity remains science's greatest detective story, a puzzle where the pieces are hidden in the fabric of reality itself. Light is the universe's ultimate sprinter. Nothing can overtake it, not even gravity's relentless pull. This cosmic speed limit, roughly 300,000 kilometers per second in a vacuum, isn't just a rule, it's the foundation of reality itself. Einstein's theory of relativity cemented this idea. No matter how much energy you pour into an object, it can never reach, let alone exceed, light's velocity. Even gravity, the force that bends spacetime and tugs at galaxies, obeys this law. Its influence doesn't spread instantaneously. It ripples outward at the exact same speed as light, in waves we now call gravitational waves. Think of it like a game of cosmic telephone. If the sun suddenly vanished, Earth wouldn't spiral away instantly. Instead, the news of the sun's disappearance would race toward us at light speed, taking 8 minutes to arrive, the same time sunlight needs to reach our planet. Until that gravitational message hit, Earth would keep orbiting an empty point in space, blissfully unaware. This delay isn't a flaw, it's a feature of the universe, ensuring cause and effect remain orderly. If gravity acted faster than light, it would shatter the very framework of causality, allowing paradoxes where events could influence their own past. Black holes offer the most dramatic test of this rule. Their gravity is so overpowering that not even light can escape once it crosses the event horizon. But here's the catch: the black hole's gravitational pull itself can't reach out faster than light to snatch things in. Instead, the curvature of spacetime around the hole dictates how objects fall inward, with every tug propagating at light speed. Even the gravitational waves from colliding black holes, which shake the fabric of the cosmos, travel no faster than the light they'll never outrun. This shared speed limit creates a strange harmony between the two forces. When a massive star explodes as a supernova, light and gravitational waves race side by side across the universe, each carrying different pieces of the story. Neutron star collisions, observed in both gravitational waves and gamma rays, prove this synchronization. Their ripples and light arrive at Earth within seconds of each other after journeys spanning millions of years. It's as if the universe insists on fairness. Gravity might bend light's path, but it can't cheat by moving faster. Yet this rule also hints at something deeper. The fact that light and gravity share a speed suggests they're not entirely separate players but threads woven into the same cosmic tapestry. Some theories, like quantum gravity models, propose that at the tiniest scales, space-time itself might flicker with uncertainty, blurring the line between gravity and light's domains. Until we crack that code, light's speed remains the unbreakable barrier, a referee ensuring the war between gravity and light stays fair, even in the universe's most violent arenas. The holographic principle flips our understanding of reality inside out, suggesting the entire universe, with all its stars, galaxies, and forces, might be a projection from a two-dimensional surface at the cosmic horizon. Imagine a black hole's event horizon, that point of no return for light, etched with infinitesimally small bits of information like the pixels on a screen. According to this theory, everything we perceive in 3 dimensions, the swirl of galaxies, the warmth of sunlight, even our own thoughts, could be encoded on this distant boundary, with gravity and light acting as translators between dimensions. It's as if the universe is a cosmic hologram, where the true workings of reality play out on a flat, shadowy canvas, and what we experience is merely the projected illusion. This radical idea emerged from studying black holes, where physicists discovered something startling. The maximum entropy, or information content, of any region of space isn't proportional to its volume, as you'd expect, but to its surface area. In other words, all the information needed to describe what's inside a black hole could fit neatly onto its event horizon, like a DVD storing a 3-dimensional movie on its 2-dimensional surface. Extend this logic to the entire cosmos, and you get the holographic principle, a framework where gravity, the force that shapes space-time, might actually be a secondary effect emerging from quantum interactions on the universe's outer shell. If true, this reshapes the war between gravity and light in profound ways. Light, the carrier of information, would be the brush painting the hologram, its photons encoding the data that defines our reality. Gravity, meanwhile, wouldn't be a fundamental force but a consequence of that data's organization, a glitch in the cosmic code, so to speak, creating the illusion of attraction between masses. Think of it like a video game. The characters on screen appear to move through a 3-dimensional world, but their actions are dictated by lines of code hidden beneath the graphics. In the holographic universe, gravity is the lag in the system, the delay in rendering that makes objects seem to pull on one another. The implications are staggering. If the holographic principle holds, it could unify quantum mechanics and general relativity by showing their 2 sides of the same coin, quantum bits interacting on a boundary, manifesting as gravity and light in our perceived reality. Experiments like the holometer at Fermilab have searched for evidence of this pixelation of spacetime, hunting for faint quantum fuzz in the fabric of reality that might betray its holographic nature. So far, the results are inconclusive, but the search continues, pushing the limits of our detectors and our imagination. What's most tantalizing is how this idea reframes the cosmic struggle we've been exploring. Gravity and light aren't just opposing forces, they're partners in a grand illusion, one weaving the tapestry of space-time while the other colors it with information. The universe, then, isn't just a battlefield. It's a projection, a story written in quantum script on the edge of existence. And if we're just shadows on the wall of a higher dimensional cave, as Plato once mused, then every star, every black hole, every flicker of light is part of a drama far stranger and more beautiful than we ever dared to dream. Entropy is the universe's silent saboteur, the unseen force ensuring that no battle, not even the cosmic struggle between gravity and light, can escape its slow unraveling. The second law of thermodynamics states it plainly: disorder always increases, energy disperses, temperatures even out, and systems march irreversibly toward chaos. But here's the twist: entropy doesn't just watch from the sidelines. It reshapes the battlefield, tipping the scales in ways that redefine what victory even means. Take black holes, gravity's ultimate triumph. Even these cosmic monsters bow to entropy's rules. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy isn't just large, it's proportional to the area of its event horizon. The more a black hole consumes, the more disorder it contains, etched into its boundary like invisible graffiti. Stephen Hawking later revealed the shocking consequence: black holes aren't truly black. They leak. Quantum fluctuations near the event horizon allow particles to escape, slowly draining the hole's energy in a faint glow now called Hawking radiation. Over eons, even the mightiest black hole will evaporate, its order dissolving into the cold void. Gravity's strongest bastions aren't invincible, they're temporary, crumbling under entropy's patient siege. Yet light isn't spared either. Every photon racing through space carries entropy with it, its energy spreading inexorably thinner as the universe expands. Consider the cosmic microwave background, that ancient afterglow of the Big Bang. Once a searing, uniform blaze, it's now cooled to just a few degrees above absolute zero, its heat diluted across an ever-growing cosmos. The stars themselves are entropy's agents, fusing ordered hydrogen into chaotic helium and scattering heavy elements into the void. Every supernova is a riot of disorder, a firework of particles flung into the abyss with no hope of return. The end game is the heat death, a state where entropy reaches its peak, and the universe becomes a featureless graveyard of equilibrium. No temperature differences, no energy gradients, just a lukewarm sea of particles too dispersed to power even the faintest glow. Gravity's structures, galaxies, stars, planets, will have long since disintegrated. Light, stretched beyond recognition by expansion, will fade into undetectable whispers. It's not a dramatic collapse or a fiery crunch, but a slow, silent surrender to the inevitable. But here's the haunting beauty of it all: entropy isn't just destruction. It's the engine of change, the reason anything happens at all. Without the drive toward disorder, stars wouldn't shine, planets wouldn't form, and life wouldn't arise. The same force that dooms the cosmos also made it possible. In the end, the war between gravity and light isn't a fight for dominance. It's a fleeting spark in entropy's infinite night, a brief defiance against the tide that will one day claim them both. And perhaps that's the most profound lesson of all. In a universe ruled by chaos, even the grandest battles are just ripples in the dark. What if our universe's epic struggle between gravity and light is just one version of an infinite cosmic drama? Multiverse theories suggest that beyond the edges of our observable reality, countless other universes might exist, each with its own unique laws of physics, where the balance between these fundamental forces could be radically different. Some might be places where gravity reigns unchallenged, collapsing every flicker of light into darkness the moment it's born. Others could be realms where light dominates, its particles so energetic that gravity barely gets a foothold, leaving matter scattered like dust in a hurricane. Take bubble universes, one of the leading multiverse hypotheses. Imagine a vast cosmic foam, where each bubble is a self-contained universe with its own physics, born from the chaotic energy of eternal inflation. In one bubble, gravity might be 10 times stronger, squeezing stars into black holes before they can ignite. In another, the speed of light could be slower, turning the cosmos into a sluggish arena where nothing moves faster than a crawling car. Some bubbles might not even have light as we know it, their skies painted by entirely different forms of radiation. The possibilities aren't just endless, they're unimaginable. Then there's the string theory landscape, which proposes a multiverse where the number of possible physical laws is in the tens to the hundreds of quintillions. In this view, the forces we see as constants, the strength of gravity, the mass of particles, even the existence of light itself, are just local bylaws frozen into place during our universe's birth. Elsewhere, the rules could be so alien that gravity and light might not even exist as separate forces, merged into something entirely new. Picture a universe where gravity leaks into extra dimensions, weakening its grip, or where light couples with dark matter, creating luminous shadows that dance through space. But here's the twist: even in these exotic realms, conflict might be inevitable. Any universe that forms structures, stars, galaxies, life, likely requires some tension between attraction and repulsion, binding and radiation. Without gravity, matter would never clump together. Without light, energy couldn't escape to forge complexity. So while the details might change, the underlying theme could persist. Existence itself may hinge on a delicate, eternal struggle between forces that build and forces that disperse. The most haunting question isn't whether other universes exist, it's whether any of them have found a truce. Could there be a cosmos where gravity and light exist in perfect harmony, their battle resolved into stillness? Or is the very nature of reality built on their rivalry, making the war we see not just a local skirmish, but a fundamental feature of existence? Until we find a way to peek beyond the veil of our own universe, these questions remain open. But one thing's certain: if the multiverse is real, then the story of gravity and light isn't just our story. It's a single verse in an endless cosmic epic, playing out in ways we're only beginning to dream of. Alien civilizations, if they exist, might see the struggle between gravity and light not as a battle, but as a symphony, an intricate dance of forces to be mastered rather than merely observed. Imagine a species so advanced that they've tamed black holes, using their immense gravity as cosmic power plants. Orbiting just outside the event horizon, they could siphon energy from the swirling accretion disk, harvesting the light and heat spat out by matter in its death throes. Or perhaps they've engineered Dyson spheres around neutron stars, capturing the intense radiation pulsed from these spinning stellar corpses, turning gravity's most extreme creations into beacons for interstellar communication. Some civilizations might have unlocked the secrets of gravitational lensing, bending starlight like a telescope the size of a galaxy to peer into the infancy of the cosmos. Their astronomers wouldn't just study the war between gravity and light, they'd manipulate it, using massive objects as lenses to magnify the faintest whispers of the early universe. For them, a quasar's jet or a gamma-ray burst's afterglow could be more than just astrophysical phenomena. They might be tools, cosmic signposts guiding their ships through the voids between stars. And what of dark energy? A society that's thrived for billions of years might see the universe's accelerating expansion not as a threat, but as a puzzle to solve. They could be building structures on scales we can't fathom, megastructures anchored in spacetime itself, resisting the pull of dark energy to keep their civilizations bound together even as the cosmos tries to tear them apart. Their physics might reveal that gravity and light are just two faces of a deeper, unified force, one that we're only beginning to glimpse in our most ambitious theories. Then there's the haunting possibility of civilizations that have already succumbed to the war's inevitable end. Worlds swallowed by black holes, their final signals redshifted into silence. Or cultures that flourished too late in the universe's life, their skies already darkening as expansion carries the stars away. They might study the fading glow of the cosmic microwave background like archaeologists sifting through ruins, piecing together the story of forces that once shaped everything and now, in the twilight of time, barely stir at all. The truth is, we have no way of knowing, but if other minds are out there, they're likely asking the same questions we are, tracing the same scars left by gravity and light's eternal duel. Whether they're builders or explorers, survivors or archivists, their understanding of these forces would shape their destiny just as ours shapes ours. The war isn't just humanity's story. It's written into the fabric of reality itself, waiting to be read by anyone with the curiosity to look up and wonder. Artificial gravity might sound like science fiction, but it's humanity's quiet attempt to cheat the cosmic rules, to bend the universe's iron grip just enough to survive long voyages among the stars. Without gravity's pull, astronauts float helplessly, their muscles withering, bones thinning, and even their sense of direction unraveling after months in microgravity. But what if we could recreate gravity's effects without relying on a planet's mass? The answer lies in one of the oldest tricks in physics: spin. Picture a rotating space station, its outer rim whirling fast enough to press objects and people against its walls with centrifugal force. This isn't gravity as Einstein defined it, but the illusion is convincing. The faster the spin, the stronger the pull. A station like the one from 2001, A Space Odyssey, spinning majestically in orbit, could mimic Earth's gravity with just a few rotations per minute. But there's a catch: spin too fast and astronauts would feel dizzy, their inner ears protesting the artificial tilt of their universe. Spin too slow and the effect weakens, leaving them in a sluggish parody of weightlessness. Engineers walk a razor's edge, balancing comfort against physics, dreaming of stations where lunar or Martian gravity could be dialed in for training future colonists. Magnetism offers another tantalizing workaround. Scientists have levitated frogs and even mice using powerful magnetic fields, proving that diamagnetic forces, weak repulsion against magnets, can counteract gravity's pull. In theory, a spacecraft could use superconducting magnets to create a gravity-like push, anchoring astronauts to floors or tools to tables without spinning a single bolt. But scaling this up for human habitats is a nightmare of energy demands and technical hurdles. Even if we cracked it, the effect would be fleeting, a fragile defiance of nature compared to the steady tug of a spinning station. The wildest ideas lie in speculative physics. What if we could manipulate gravitational fields directly, like the fictional gravity plating of Star Trek? Some theories suggest exotic matter or condensed energy could warp spacetime locally, bending it just enough to simulate a planet's pull. Others toy with quantum effects, where entangled particles might transmit gravitational influence across distances. These are dreams for now, but dreams grounded in real science, where the line between impossible and improbable blurs with each breakthrough. Every experiment, from spinning centrifuges on the International Space Station to magnetic levitation labs on Earth, is a tiny rebellion against the universe's rules. We're not just fighting bone loss or nausea, we're probing the limits of what it means to live beyond Earth's cradle. Because if humanity is ever to thrive among the stars, we'll need more than rockets and oxygen. We'll need to trick the cosmos itself into giving us a foothold, a patch of artificial ground in the endless dark. And in that struggle, we're not just escaping gravity's grip. We're learning to dance with it. Light sail technology flips the cosmic duel between gravity and light into an engineering marvel, proving that even the faintest photons can propel humanity beyond the solar system. Picture a spacecraft with no rockets, no fuel, just an enormous mirror-like sail thinner than a human hair. When sunlight strikes its surface, the photons transfer their momentum, pushing the sail forward with gentle but relentless force. It's not science fiction. Missions like Breakthrough Starshot aim to use this very principle to send tiny probes to Alpha Centauri at 20% the speed of light, riding on laser beams instead of chemical combustion. The genius of light sails lies in their simplicity. Unlike traditional rockets, which fight gravity by burning massive amounts of fuel, these sails harness light's inherent energy, the same radiation pressure that comets' tails have been pushed by for billions of years. Japan's Ikaro's mission proved it could work in 2010, becoming the first spacecraft to successfully deploy a solar sail and cruise through space propelled purely by sunlight. But Starshot's vision takes this further, swapping sunlight for ground-based lasers that could blast a sail with concentrated light, accelerating a gram-scale probe to velocities no chemical or ion engine could ever match. Yet light's pressure is a fickle ally. The farther a sail travels from its light source, the weaker the push becomes a challenge that turns interstellar journeys into high-stakes races against time. To escape gravity's grip entirely, a sail must reach solar system escape velocity before drifting too far from the sun's rays or the laser's focus. That's where materials science steps in. The ideal sail must be ultralight yet durable, reflecting nearly all incoming light to maximize momentum while surviving micrometeoroid impacts and the blistering intensity of concentrated lasers. Some designs propose graphene or metamaterials that could self-repair minor tears, like a spider weaving its web anew in the void. The irony is poetic. Light, which gravity bends and black holes swallow, could become our ticket to outmaneuvering gravity's pull altogether. Future sails might even ride the solar wind or cosmic radiation, tapping into the same forces that once seemed like immutable barriers to exploration. And while today's prototypes are modest nanoscale chips attached to handkerchief-sized sails, the implications are cosmic. Imagine fleets of sails mapping nearby exoplanets or relay stations beaming data back to Earth from the edge of interstellar space. This isn't just about escaping gravity, it's about rewriting the rules of the game. For centuries, we've fought gravity with brute force, building taller rockets and heavier engines. Light sails offer a subtler strategy, turning our star's own energy against the forces that anchor us to our celestial cradle. The war between gravity and light isn't just happening in distant galaxies or black hole mergers. It's unfolding in laboratories and launch facilities, where engineers are proving that sometimes the gentlest push can break the strongest chains. The first ever image of a black hole wasn't just a photograph, it was a cosmic coronation, capturing gravity's ultimate victory over light in stunning detail. When the Event Horizon Telescope collaboration unveiled that now iconic orange ring in 2019, the world witnessed something philosophers and scientists had debated for centuries: the shadow of a singularity, a place where gravity doesn't just bend light but consumes it entirely. That glowing donut wasn't the black hole itself, it was the warped ballet of photons spiraling around the event horizon, their paths twisted into a halo by gravity's irresistible grip. Creating this image required an astronomical feat of engineering. The Event Horizon Telescope wasn't a single instrument, but a network of 8 radio observatories spanning the globe from Hawaii to Antarctica. By synchronizing these dishes with atomic clocks, astronomers effectively built a virtual telescope the size of Earth itself, a technique called very long baseline interferometry. For days in April 2017, these stations trained their gaze on Messier 87, a supermassive black hole 55 million light-years away, collecting petabytes of data. The challenge, the signal they sought, was buried in noise, like trying to hear a whisper in a hurricane. It took 2 years of supercomputer processing and painstaking analysis to tease out the hidden pattern. A ring of light precisely the size Einstein's equations predicted. What makes this image so revolutionary isn't just its beauty, it's the science hidden in its asymmetry. The brighter lower half of the ring reveals light being Doppler boosted toward us as material swirls around the black hole at nearly light speed. The darker upper section shows photons fighting against the flow, their energy drained as they climb out of gravity's well. This lopsided glow is gravity's signature, a real-time demonstration of how space-time warps under unimaginable mass. Even the shadow size, about 2.5 times larger than the event horizon, matches predictions about how black holes magnify their own darkness by bending nearby light paths inward. But perhaps the most profound lesson lies in what we didn't see. No light escapes the shadow's center, a perfect circle of nothingness where gravity's triumph is absolute. This absence confirms a cornerstone of general relativity. The event horizon isn't just a theoretical boundary but a physical point of no return. The image also silenced lingering doubts about whether black holes truly exist as Einstein envisioned. Before this, even some physicists wondered if singularities might be mathematical quirks rather than real cosmic objects. Now, we have visual proof that nature's most extreme prediction is out there, warping the fabric of reality. Since that first image, the Event Horizon Telescope has captured even sharper views, including the Milky Way's own supermassive black hole, Sagittarius, a star. Each new observation peels back another layer, revealing how magnetic fields channel jets of plasma or how black holes flicker as they devour matter. These aren't just snapshots, they're frames in a cosmic movie, showing us gravity's relentless dance with light in real time. And as technology improves, future images might even capture black holes in motion, their shadows wobbling as they spin or collide, turning theoretical equations into visible reality. That glowing ring, forever circling the void, is more than a scientific milestone. It's a reminder that even in darkness, light finds a way to tell its story. The photons that formed that image began their journey before mammals walked the Earth, traveling 55 million years just to etch gravity's victory onto our telescopes. And in their final moments as they curved toward oblivion, they gave us something extraordinary, not just a picture, but a front-row seat to the universe's most awe-inspiring spectacle. Neutrinos are the universe's ultimate rebels, ghostly particles so indifferent to gravity's pull that they pass through planets, stars, and even black holes without a second glance. Born in the hearts of exploding stars, nuclear reactions, and cosmic collisions, these nearly massless wanderers carry secrets from the most violent events in existence, yet they slip through matter like shadows through a sieve. While gravity bends light and warps space-time, neutrinos laugh in the face of such forces, traveling billions of light years without deflection, absorption, or even a trace of interaction. They're the cosmic wild cards in the war between gravity and light particles that refuse to take sides. Take a supernova, for example. When a massive star collapses, most of its energy erupts as light, but a staggering 99% is actually carried away by neutrinos in a pulse lasting just seconds. These particles blast outward unimpeded, while photons struggle for hours or even days to escape the star's dense, gravity-choked debris. In 1987, when a supernova lit up the Large Magellanic Cloud, detectors on Earth caught a fleeting burst of neutrinos 3 hours before the visible light arrived. It was proof that these phantoms outrace even light itself when gravity's grip is at its tightest. But neutrinos don't just ignore gravity, they defy it in ways that challenge our understanding of physics. Billions of them pass through your body every second, relics of the Big Bang, the sun's nuclear furnace, and distant galactic cataclysms. Yet detecting them is like trying to catch smoke with your hands. Massive observatories like IceCube, buried deep in Antarctic ice, or Super Kamiok, and a tank of ultra-pure water beneath a Japanese mountain, wait for the rare moment a neutrino collides with an atom, releasing a faint flash of light. These detectors are less like telescopes and more like cosmic tripwires, revealing the paths of particles that have traversed the universe unscathed. What makes neutrinos so invaluable is their unflinching honesty. Unlike light, which can be scattered, absorbed, or bent by gravity and matter, neutrinos arrive pristine, carrying unfiltered information about their origins. When a black hole shreds a star in a tidal disruption event, or when two neutron stars collide, the light we see is often distorted, delayed, or obscured by dust. Neutrinos, though, deliver the raw story, a timestamp and a roadmap straight from the carnage. They're the universe's encrypted messages, immune to the noise that scrambles other signals. Yet even these phantoms have their limits. Neutrinos oscillate, changing flavors between electron, muon, and tau as they travel, a quirk that implies they have some mass, however vanishingly small. This discovery, which earned the 2015 Nobel Prize in Physics, hints at a hidden layer of particle behavior that might one day bridge gaps in quantum theory and gravity's domain. It's a reminder that in the cosmic war between light and gravity, even the most aloof particles can't escape the universe's deeper rules. The future of neutrino astronomy promises even wilder revelations. Proposed detectors like the Pacific Ocean Neutrino Experiment aim to turn entire ocean volumes into neutrino telescopes, while Dune, a massive underground project in South Dakota, will study neutrino oscillations with unprecedented precision. These experiments could unlock mysteries like the inner workings of supernova, the nature of dark matter, or even the conditions of the universe's first second. Neutrinos might not bend to gravity's will, but in their defiance, they've become our silent guides, whispering truths from places light can't reach, and proving that sometimes the best way to understand a battle is to follow the particles that refuse to fight. The next chapters in the cosmic war between gravity and light are being written right now, not in the distant reaches of space, but in laboratories and launch facilities across Earth. A new generation of telescopes and experiments is gearing up to probe this ancient conflict with unprecedented precision, peeling back layers of mystery that have persisted for centuries. At the forefront is the James Webb Space Telescope, already revolutionizing our view of the early universe. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb's infrared eyes pierce through cosmic dust, capturing the faint glow of the first stars and galaxies as they wrestled free from gravity's grip. Every image it beams back is a time capsule, showing us how light fought to escape the crushing density of the young cosmos, carving out transparent bubbles in an otherwise opaque sea of gas. But Webb is just the beginning. The Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s, will take the battle to gravity's domain. This trio of spacecraft, orbiting in a perfect triangle millions of miles apart, will detect gravitational waves with wavelengths too long for Earth-based observatories to catch. Imagine listening to the universe's bass notes, the slow-motion mergers of supermassive black holes, the ripples from cosmic strings, perhaps even echoes of the Big Bang itself. These waves will reveal gravity's hidden victories, tracing how it warps space-time in ways light alone could never show. Together, Webb and LISA form the ultimate tag team, one mapping light's escape from gravity's grasp, the other charting gravity's invisible ripples through the cosmic fabric. Meanwhile, groundbreaking experiments like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will scan the entire southern sky every few nights, catching fleeting moments where gravity and light collide. When a distant star's light flickers as an unseen planet passes in front, or when a supernova's glow is magnified by a foreground galaxy's gravitational lens, these events become cosmic laboratories. They'll help measure dark matter's distribution, test alternative theories of gravity, and even hunt for primordial black holes, remnants of the universe's infancy that could rewrite our understanding of how structure formed. And then there's the wild card, quantum gravity experiments. Facilities like the holometer at Fermilab and future quantum computers aim to simulate space-time at the smallest scales, probing whether gravity and light share a common origin in the frothy quantum foam. If successful, they might reveal how gravity's pull emerges from the same quantum rules that govern light's particles, bridging the chasm between Einstein's relativity and quantum mechanics. The most exciting part, these missions will uncover phenomena we haven't even dreamed of yet. Every time humanity has built a better telescope or detector, it's stumbled upon something utterly unexpected: black holes, dark energy, gravitational waves. The next breakthroughs could reshape the very narrative of this cosmic war, showing us that gravity and light aren't just adversaries, but partners in a dance far more intricate than we've imagined. The universe's greatest story is still unfolding, and we're finally turning the page. At its core, the cosmic struggle between gravity and light isn't just about equations or celestial phenomena. It's a mirror reflecting humanity's own existential tensions. Gravity, with its relentless pull toward unity and collapse, echoes our deepest fears of entropy and oblivion. Light, defiant and illuminating, embodies our yearning to transcend limits, to be seen and understood across the vastness of time and space. Together, they frame a paradox that has haunted philosophers and poets alike: the tension between attachment and liberation, between the weight of existence and the urge to shine beyond it. Consider how gravity shapes not just stars but stories. Ancient myths often portrayed the heavens as realms of perfect, unchanging order, until Galileo's telescope revealed moons orbiting Jupiter, proving celestial bodies could bind one another in motion. That revelation didn't just upend astronomy, it shattered the illusion of humanity's central place in the cosmos. Gravity's universality humbled us, showing that the same force guiding an apple's fall also orchestrates the dance of galaxies. Yet light, in its boundless journey, offers a counterpoint. Every star we see is a beacon from the past, its photons traveling millennia to reach us, insisting that even in a universe governed by gravity's pull, connection across unimaginable distances is possible. This duality resonates in art and culture. Renaissance painters used chiaroscuro, the interplay of light and shadow, to evoke depth and drama, unknowingly mirroring the cosmic balance. Gothic cathedrals stretched skyward, their spires defying gravity in stone, much like light defies collapse in the heart of a star. Even modern metaphors lean on this conflict. We speak of gravitas to describe weighty importance, or illumination to signify understanding. The war between these forces isn't just physical, it's woven into how we make sense of meaning itself, but the most profound lesson lies in their interdependence. Without gravity, light would have no stage, no stars to birth it, no black holes to bend its path. Without light, gravity's work would remain invisible, its cosmic architecture hidden in darkness. Their rivalry creates the conditions for complexity, for life. On Earth, gravity holds our atmosphere close while sunlight fuels every living thing. In the cosmos, their balance allows galaxies to spin, planets to form, and atoms forged in stellar furnaces to someday become part of eyes that gaze back at the stars. Perhaps then, the war isn't a conflict to be won but a dialogue to be cherished. Gravity reminds us of our fragility, how easily we could be crushed by a black hole or scattered by entropy. Light whispers of resilience, carrying stories across epochs long after their sources vanish. Together, they teach us that existence isn't about choosing between anchor and wings, but understanding how both shape the journey. Every time we measure a star's redshift or marvel at a gravitational lens, we're not just doing science. We're reading a love letter from the universe, written in the language of forces that refuse to let go and refuse to stay silent. The universe is a battlefield, but not one of destruction instead. It's a stage where gravity and light perform an eternal dance, sculpting everything from the tiniest atoms to the grandest galaxies. This cosmic conflict has left its mark everywhere, in the silent darkness of black holes, the rippling whispers of gravitational waves, and the faint afterglow of the Big Bang itself. These remnants aren't just relics, they're clues, helping us piece together the story of how the universe came to be and where it might be headed. What makes this struggle so profound isn't just the science, it's the sheer beauty of its consequences. Without gravity's pull, stars would never ignite, their light trapped in clouds of gas too scattered to fuse. Without light's relentless energy, gravity's structures would remain invisible, hidden in the dark. Together, they've woven the fabric of reality, creating a cosmos where planets orbit, galaxies spin, and life itself becomes possible. Every sunset, every aurora, every shimmering star is a testament to their delicate balance. And the most incredible part, we're just beginning to understand it. Every new discovery, whether it's a distant quasar's jet, a neutron star's pulse, or a gravitational wave's ripple, adds another piece to the puzzle. These aren't just abstract concepts, they're windows into the universe's inner workings, showing us how the laws of physics play out on scales both unimaginably vast and infinitesimally small. But this isn't just a story for scientists, it's a human story, one that connects us to the cosmos in ways we're only starting to grasp. When you gaze at the night sky, you're seeing the aftermath of this epic struggle. The light of stars that fought gravity's pull to reach your eyes, the shadows of galaxies shaped by dark matter's unseen hand. You're witnessing a war that's been raging for billions of years, one that will continue long after we're gone. So keep looking up. The universe isn't static, it's alive with motion, with conflict, with creation. New chapters are being written every second in the birth of stars, the collision of black holes, the expansion of spacetime itself. And as we keep exploring, we're not just uncovering secrets, we're learning to see the cosmos not as a cold, empty void, but as a dynamic, ever-changing masterpiece. The greatest stories aren't just out there, they're unfolding all around us, waiting to be discovered.